Okay. Just like we recall part of our previous lecture, we talked about the source code of right here. We always say facing the question about like reader, writer, like producer, consumer, this type of question. So probably also maybe in your exam you'll see some question, but you don't have to really write the complete code. Or like I will give you partial it, so you don't have like finish everything, but you need to remember. If I tell you, let's say most of the time we get the like receive, produce, or like under the inside loop. Then how can we send the signal? So if you remember the C rate, signal, receive, so all these functions. So when can we check? Like when we grant the access, how can we make sure we lock it? Like for only this specific process. So after I finish it, I need to release it. So we have different cases. So you just need to remember when do you need to call those things and then execute a critical section. So we just ignore the critical section. It can do anything, but it's like who can grant this one, especially we have multiple processes. Okay. So last time we talked about that, like the message passing, and then this time we will also talk about the like operating system. So right here, we have a different approach when they come like stop, either one like shall start again or they have gone. So we need to check. So we talk about the deadlock. So the deadlock either like for the system resources when we try to communicate each other, so putting blocking each other's. Okay. So we know, so when we enter the state of a deadlock, we need to know, so it's permanent. And then we have no efficient solution to handle it. So because we're checking, here's a graph showing it's possible because let's say I need to using a C and B, and then I need to use B and C, and then A and B, and D and A. So when they try to cross it, actually when it comes in, nobody can use it. Okay, so because they are stuck on this status, I need to wait until D is free. I need to see like everyone's waiting each other, but we have no way to release it. Okay, so maybe we need to have some mechanism to avoid the deadlock. So this we need to learn. This is what the OS we do, like based on resources or the possible resources, maybe CPU bandwidth, maybe some memory, some data. Okay, so one part of the OS like we always say, we try to predict, like we try to use like log like to prevent it. And when we, is it possible that we enter the deadlock? Yes, always. When you're using Windows, Mac. So when you freeze, like nothing can click on it. So we enter the deadlock. How can we solve it? Sometimes like when we enter this stage, we start your computer. How shut it down and we start it. Okay. So I would say learning operating system is like accept it. So because the system architecture is like sometimes not perfect, or we also need to know is like not the application we are developed by different developer company. So sometimes they grant the access, they get the lock, right? If they forgot to release it, then we have like called the starving, then we are waiting for it, then it's a problem. So we see the chance. So they want to get the resources, then we will enter the deadlock. If we didn't have a deadlock, that means like when we progress, like they can get what they want and release it in time. So right here we have category about that we call that reusable resources. So can only use by you be used by one process at a time. So they're not like by use process obtained, then later free resources. Let's say CPU, IO, memory files. So they are used. Or we have consumable resources. So we create or destroy. One is they produce and consume, and then usually one process produce the resources and another one consume it. So it's that one, and then once consume it, it can not be used again by another process. Okay, it's possible. So interrupt, signal, message, IO buffer information. So that's what we use. I call it consumable resources. Okay, if I ask you, can you give an example what's usable resources CPU? Okay, or like consumable, so interrupt signal. So you need to know the terms. So right here, what's a possible example for reusable? We have a request like D log dot request T, and like this, and then perform some function. So right here will be reusable for the CPU. Maybe we need to IO. Let me see. And now for the memory, so memory, let's say the space available to allocate to 200 megabyte, and then the sequence like event occur, like request 80, 60, 70, 80 to process. So if they occurred both the process like to their second request. So here things like mainly, let's say after 80, total is like 200, right? So if process one takes 80 and the next one will takes like 70. So why now it takes like 150. So neither one of them able to go to the second one because we don't have enough resources. Okay. Then we need to actually for the OS, sometimes we need to prevent or like predict the next stage. If I let them to grant like 80 for the like process one and process two get 70, what's the next stage? Can we assign 60 or 80 to the next process? So this the OS need to do, like for the management. So if they didn't do it, then we occur the deadlock, or like what's the mechanism? Like you need to check, like is it enough or not enough? That we discuss later, or like the consumable resources. deadlock. So right here, so we remember there's a pair. We have the like receive and send, or like produce and consume. That's what we did. So each process try and then receive a message from other process and then send a message to other process, receive and send it, right? And then receive and send it. So if the receive is blocking, so we couldn't receive anything, then we cannot send it. So same will occur the deadlock. So right here, let's say I have a process one request the RA, and then maybe the P1 help by the RA return back. And then the circular wait. So we send it request RA and then say help by P2, or like the resource B right here, RB, and then help by P1, and then we when we request it. Okay. So when we need to prevent the deadlock, you will see right here when I try to request it, and then only that help by P2, maybe just one, and then maybe I have two right here. I have only one for P1 holder resource B, but we still can request it for one. So we need to based on the resources what we have. Okay, so that's how the actual deadlock works. And then the resources allocation, if you look at the graph, let's say we have the resources A, B, C, D, and then we have the different process 1, 2, 3. So right here I reserve A to the program one, and then I send it request for RB, and then maybe the resource pass to the process 2. So you see that we have a flow and go back to the beginning. So we need to like have a flow, and then we know the person based on the state. Okay, and we need to think about then what's the possible condition like for the deadlock. So once the code we call the mutual exclusion. So you see all the example code showing like how can we check it, and then there is like only one process may use resource at a time. No process may access a process until that has allocated to another process. So we always say the mutual. So always make sure. That's why we always like log like release curl like get it, or like hold and wait. So process may hold allocate resources while like awaiting assignment of other resources. Also like no preemption, and then no resources can be like forcibly removed from a process holding it. So most of like this, they're necessary but not sufficient for an actual deadlock. So for actual deadlock, we have like circular wait. That means like circular is like we are waiting, A waiting for B, B waiting for C, C waiting for A. So that's why we enter the deadlock. So it's called a closed chain process exists such that each process like hold at least one resources need to be next process in the chain. That's how we know how it's going to work, like happen the deadlock. Then we should think about how can we deal with it. Okay, so we have three general approach. Right now is a prevent. Okay, deadlock adopting a policy that eliminates one of the condition. 1 through 4. Okay, or like we try to avoid the deadlock by making the appropriate dynamic choice based on the current stage of the resource allocation. Also detect, just like detect the person's deadlock, like condition like 1 to 4, like this. And then the circular chains allocate actually exists and take action to recover it. So it's the one thing right here. So this is a detailed graph you will see like for, let's say we have a prevention approach. So conservative under the commit resources, this on the allocation policy. So what is the different scheme? Let's say this one requesting all the resources at once. Okay. So I will base on if I need to use the ABC, then let them request at one time. Don't let them do it like in a sequence, so that if you remember just like this, like put it right here, like request. So when they send a request, let me know total how many. In the beginning, if I know in total I will request, let's say this one 140, then just send me 140. Don't make it as a 2 different requests. Okay. And then I know, okay, 200 and aside for process 1, then I just let the process 2 just wait or hold, then waiting in the queue. Then once it complete, release the resources, or let's say I can able to release after I finish the first function. Let's say like this, and then I can release 80 megabytes. Okay, then I can release it. Then right now I have 80, and then plus the rest will be 60. Okay, maybe I will enough for the next process. Okay, predict. Then I will let it assign this resource to process 2. Let it execute. Okay. So it will be right here. So when if we're doing this one, like well for all processes that perform a single burst of activity and no preemption necessary, and then but what's like inefficient? Here's a problem. Because when we always talking like multitasking, multi-threading, here's a purpose. It's like we want to like let them do it like concurrently, right? In the same time, so we want to divide them. But if we just like every time like request all the resources at one time, occupy everything, then it's meaningless. So that's why we delay the process. Also, like for future resources requirement must be known by the process. That means I need to know what I'm going to use later. Okay, so it's not a benefit thing. What's the next? And then second, if we need to know what's the advantage apply, so it's more like convenient when we apply the resources whose like the stage can be saved and restored easily. But also this one will be more than necessary. But we need to like easy to save and restore. And then ordering next one. So and all like we need to enforce like within a compliant time check, but also we just no runtime computation. So we need to solve it in the system design level. So this one, but this one can is like disallow the incremental resources request. So that means that when I in the system design level, I already decide how many. But later, if the function I need to request more, no way, you're not allowed to do that. So this. So how can we try to avoid sometimes like midway between like the detection and prevention? So this how can we avoid? So we try to find the like at least one safe path. So the OS like we try to predict the next stage is like we try to make sure I find a path like organizing. Okay, if I in this moment or this is how we check we are multi like P1 to Pn. If let's say if I assign the results like this, it's working. Then how about next stage? So after I assign this one, if I need to execute next stage, is it going to work or not? So if no, then I'm not doing this work. I will change it. Okay, and then I'll try to figure out another thing. That's how the deadlock sometimes really happen. Even you see like we are using, but we still have a problem of deadlock, right? That means like we sometimes not able to, we cannot guarantee 100% to find a safe path, even nowadays. So always the same, restart your computer. So like this. And then next is detection. So for liberal, and then request the resources and grant where they possible. So when just like we do the detection. So for detection, we know so we won't delay the process initialization and facilitates the online handling. So that's what we do for. Right. And then for the deadlock like prevention. So right here, for the paper, what's the possible strategy and then the condition for the deadlock. So when we design the system, so there's a possibility that in excluder. So two main methods, we have the indirect and direct. So indirect, that means like prevent the occurrence of one of the three necessary conditions. Direct prevent the occurrence of the circular weight. Circular weight, if you know, access the. So here the circular weight, like I need to get the resources, but I will help by another process. So this is gonna happen. Okay. So we have the one always apply like in the example we talk a lot we call a mutual exclusion. So this one is that it cannot be like disallowed and the access resource that require mutual exclusion. So they must be supported by the OS. Okay. It can be the OS not supported, but depends on. But most of right now nowadays, because when we allow like multitasking, we should support this one. Hold and wait. So only like require process, like require all the resource it will need at one time. There's doing, and then pause the process until all requests can be granted simultaneously. Okay, and it's inefficient. So process may be held for a long time before beginning. So resources may be held for a long time, but only used for a short period. So there's a we need to have a mechanism. I think about if this process like for the runtime. When we need to think about it. Let's say this process to execute maybe just it takes 1 second, but I need to grant a lot all the resources. But when we are trying to like the OS to manage it, you say okay, you need to get this one, but when we execute this process, I allow me to execute 3 process, or like when have new process comes in, yeah, I think we have better performance. Then this process will hold forever. Yeah, so we never execute. Even it's just a subprogram, then how can we let it? Then we can think about that later. Okay, so no preemptions, and then if a process like holding certain resources, so it's denied for the request, then the process must release its original resources and then request them again. So if we are not running, then we need to release it. So they may be preempt the second process and request it release its resource. So it's possible, not only P1 or maybe P2, P3. So keeping to this. It may be have a circular wedge that define linear order of our resource type. So this is going to happen. And then for avoid. So just like able to do the 2 different approach, and then for the decision, so we try to make a dynamically like whether the current resource allocate request will then granted. So if we grant it, is it possible to have that out? If yes, it will, then we don't do that. But we need to know is like we have the knowledge. So we need to know this process, like what's going to happen next. Then how? So the first one is that do not stay a process if its demands may lead to deadlock. Okay. And then that means this one is like the process initiation denial, and do not grant an incremental resources request to the process if this allocation may lead to a deadlock. So this one is like when we execute. So do you allow them? Let's say we execute P1, but when we execute for the certain statement, it requests to more memory. Let's say more memory, but you don't have enough. Then we don't allow to answer. I thought maybe we need to put this process to a waiting or hold it in the queue, wait maybe somewhere to release it. We know okay, it's safe, then we can do it. So always like avoid it going to happen. And then initialization. So don't start the process unless all the maximum can pass those like current process can meet. So that's we're going to do. Also must specify up like the from maximum needs for all resources definition. So right here, like for now, let's say for we have resources R, right? R1 to M, and then availability V1 to VM. So when we claim it, it's a matrix, So it's showing okay. So the C11 to CNM, allocation A, maybe 11 to NM. So you see total the resources in the system, and then maybe the each resources not allocated to any process, you will see right here. So let's say if they request that process I from resource J, I1, and then the IJ is the process J like this. So this one is the allocation is like current A. So you see it's just a metric showing how it matching and allocate. And for the denial, we need to refer to the called the banker algorithm. So the state of the system, we need to refer the current allocation of the resources process. and then save state. So if this one I will try to prepare that for next time, so you know what's the stage and save state. So it's one which is like at least one sequence of resources allocation to the process. So do not result the deadlock. So it's called a save state. And unsafe is like not safe. Simple. And how can we determine the safe state? So when the state of system considering let's say 4 processes and 3 resources, then we need to allocation make like 4 processes. We need to check like right here, let's say we have the amount of existing resources right here, 3 which are available after the allocation. So we have like 9, 3, 6, and minus in this one maybe for the which one P1 like 3, 2, 2, then we assign, and then you will see right here. I mean, actually, so in the claiming, let's say for the process 1, for resource 1, we need to claim like 3, 2, 2, and then process 2 we can 6, 1, 3, and then process 3, 3, 1, 4, and then 4, 2, 2. So here's the first matrix we need to claim. And then for the allocation, okay, so if I want to allocate, let's say get the right now for the P1 I get resource 1, okay, so and then P2 6, 1, 2, and then P3 when I 2, 1, 1, yeah, less, and then P4 0, 0, 2, okay. And then when we try to make is like matrix claim matrix C minus A. So you after minus it, so it's be 2, 2, 2, and then 0, 0, 1. So 1, 0, 3, and then 4, 2, 0. So right now is the current status. And then the available, you'll see when we get a 2, 1, 4, 7 total, and then here's a 4. Then also R3, then we need to get maximum 5. So we need to check maximum. But for the certain stage, and then after we minus, then we will see the remaining. We'll show you more the status. So start with here, and then let's say we request stuff with the 1, and then allocate the matrix 8. Or like maybe if we need to request more than 2, 2, 2, then maybe we'll minus it 2, 2, 2. And then do you see the completion? We will release it after the 2 complete, we release it. So right here, 6, go back. But this one we will showing, I will try to prepare the example or like the program you can execute. See, and then right now after the P3 execute, and then we clean it. So we like 3, 1, 4, and then release, and then we clean it all the 0, 0. So right now for the P4 remaining will be 4, 2, 2, 0, and then allocate right now it's 2, let's say we have 4, 2, 0. That's what we need. And then you will see the 3 right here. So here's the overall pictures of it. Later, if I have a lab, then I will try to cover more details. And basically, when we have a logic, so you will see when we declare like for implementation, we have a struct and create a state, and then we have resources available, and then claim and allocate. So it's the same as array, and then claim and allocation will be a 2D array. And first of all, we always check like, do they pass it? Is it bigger than the claim? If no, then we can check the next one. If yes, then have an error. So we cannot let the total request more than the claim. And next we check, okay, right now is the request is current is bigger than the available. So if yes, then we will suspend, wait for it. If no, then we can check the end of the state. So let's say if it's okay, then we will define the new state and then allocate it. So this one will be the allocation plus the request plus it, and available minus request, how many? So will be the allocation and available, basically. So right now, if we are okay, we are just like putting the safe state, carry out the allocation. If no, then we store to original and suspend the process. So that's how we keep checking the status. You will see we call the function the if state of new state when we pass it, and the program we have the integer, the current variable like the m is a 1D array, and then we just process the best number of process. And based on the current available, so we just like equals the available right here. Here's the available array right here. So it's the m. So how many they are available? And then check. So for the rest will be all the process right here, and then set it is a possible by default. So we are checking. So if it's a possible, then we check. Okay, check the process in the rest, like claim minus the allocation. So is it less than the current availability? Like if we find it, then we just like okay, allow it to the current plus the allocate. So we've added to the current. And then for the rest, we minus the value. We're gonna, if we are able, just like keep doing that. If no, then we just set to false. And then rest will be equals to no. So it's okay, nothing going to happen. If yes, then we just like assign minus it. So it's the algorithm we're going to use. And what's the advantage for this one doing? So we are not necessary to like preempt or like roll back the process as a deadlock detection, and it's less restrictive than the deadlock prevention. So here's the advantage. So the deadlock avoidance like restriction right here. So we can like maximum the resource requirement for each process must stay in advance, and then process under the consideration must be independent and with no synchronization like requirement. So we synchronization, that means that we execute at the same time. And there must like fixed number of resources to allocate. So this one also no process may exist while holding the resource. So this like restriction, so we need to know. And deadlock strategy. So right here, for the deadlock prevention strategy, like conservative and but restrictive. The reason we need to be restrictive because we need to prevent like 1 to 4 what we mentioned before. And then for the opposite extreme, so deadlock detection, so does not like impose the limit of the for prevention, then we don't have a restriction of it, just like detecting and avoid. For deadlock avoidance, just like in between, less restriction, but also we still have some, so just no in between. So it depends on the need. When we talk about the detection, so we have the deadlock detection, just like the strategy really conservative, but they solve the problem by limiting the access to the resources and imposing the restriction. So we'll see. So for this one, for the avoidance, so avoidance of strategy, so we have the less restrictive, right? But we have the overhead need to dedicate or at least estimate of resources. So that's how we need to know. But if you want to avoid, then we need to know, okay, in total, how many resources we need to use. So as a opposite extreme, so as a deadlock detection. So when the deadlock detection, when we request the resource grant to process whenever they are processed. So that's why we keep checking. So it's okay to go to the next stage. If yes, we can do it. If no, just like ignore it. So this more like a prevention. So periodically, the OS will prefer algorithm. So they will allow it to detect the circular weight condition. So it's like, is it going to happen a circular condition? If yes, then we will say, okay, it's the deadlock. So we're not going to do it. If it didn't have a circular then condition, then we can execute for the next stage. For detecting this one, the algorithm just like make frequently and make sure the resources request like less frequency and depending on how likely the deadlock to occur. So this one, what's the benefit? The advantage, we can have an early detection. So we know in the early stage. So it's relatively simple. And this advantage, we need to frequently check the consume and considerable process time. So for detection, that means we need always like keep on checking. Is it going to happen before it? Okay. So for this one, let's say we have a same request matrix right here and the allocation matrix in current state. And then the resource vector right here, resource 21, 21, 21. And then available vector right here, let's say the out one, when else just one. First, like we try to mark all the process like as a row of allocation matrix of like or 0. And then initialize the temporary vector W. So and make it equal to the available vector. So make sure like equals to the available vector. So for the index I, so start from the process. So we are representing the process. So like a market. So then there is row key of less than or equals to W. So right here. So I is the process and K is the row. So the column. So make sure it's like less than that one column. So make sure the K is like in between 1 or M is the range of it. So okay. So no such row is found. So terminate the algorithm. So it works. So if we found it, that means we can add it. So it's like W plus A is to K. And then we go back and keep searching one by one. So right here we have come back with the request matrix 01, 001, 1, 001, 01, and 1, 1, 001, like this. And then right now the allocation is right here, allocation current state. And then the resource vector is 21121. So you see have the same, and then the available 001. Okay. First, we need to make the allocation matrix or 0, and then say so for the other steps. For later, I will try to have a sample program, so have a better steps to simulate. Because for the PowerPoint, maybe really hard for you to understand. I will try to cover all these detection algorithm in using the real program, so it will be easy to capture this idea. Just like for today, just let you know the theory, understand. And we try to do the recovery strategy. So when really have like that was really possible, maybe we do the abort all the deadlock process, back up each like deadlock process to some previous defined checkpoint like in certain state, and then we start all the process and let it do again. So this is how the operation I'm always doing. So success the aborted deadlock process until the deadlock no longer exists. Okay, so actually the OS is always like happen doing this way. So we will try to do the action. I try to apply the avoidance, and also try to apply if really going to happen. How can we apply the recovery? And then once we go back, like trace back to a certain stage. Okay, this one is fine. Then we can check it again. But is it possible to enter the deadlock again? Yes, it's possible. Then we do like repeat all the process. So here's the deadlock approach. It's the same. So we just skip it. And then dialing philosopher is a problem. So here's what's the deadlock. So right here we have the dialing people did this one probably. So it's let's say we have the condition and no two philosophers they can use the same fork at the same time. Also, we have no philosopher must starve to death, like avoid the deadlock in the step with it. Then if you want to like create this one. So if you look at the graph, like let's say we have the process like 1, 2, 3, 4, 5, right? So every of them they have the fork. So they need to use. So because they can choose either left or right. Like in this example, we can choose either left or right. So they cannot use the same. Okay. So they make sure they only use one. So none of them they can share. Okay. And then also they must stay starve to death. So they cannot wait forever. So that means I need to put down the fork, like let others to use it. Okay. If you remember, we talked about the semaphore. So when let's say we have the fog, let's say we have 5. So in the beginning, they're all available. And then we will have the like philosopher, let's say which one. And then for 2, we are keeping thinking. Thinking is ideal for waiting. Okay. So waiting for it. Okay, wait. It's loop. And then when we are waiting, okay, can I access for the fog? Am I able to get it? Okay, yes, I'll do it. If just like keep waiting, I can do it. If yes, and then check the next one. So this one is the round table modules. I think last time we have a student asked me to explain more about the modules. So it's getting the remainder. Okay. So last time I see something like if I have a variable n and then modules by m, so I will equals to what? So let's say I have a 10. So the modules will be the remainder of always like from 0 to 9. Okay. And then if I change to module by 2, so what are the possible grading by 2? Yes. Okay. So it's either 0 or 1. And also this one we can actually I want to let you to do it as a discuss, so we can do something for fun for practicing. So if let's say I have a value, if I need to convert that number to like a binary, then how can we do that? We can use the modules to check it. So you can think about it, and then if you're interested, I can post it as a discussion. You can put it as a bonus if you can post the result. How can you convert a number? Let's say I want to convert 10 to a binary. So what's the value? It should be 1 0 1 0. Okay, yeah. So how can you change from the decimal number to the binary? So how can you do that? And you can think about the right program just for practice. And let's say I input the decimal number, how can you convert to the binary? Okay, so right here, and I will keep it checking, waiting for this for is the next one is okay. Can I get, because you when I'll get my current one or the next one. So if you remember the table, so let's say I'm waiting for this one or the next one. So if no, if I can either like pass either one of the weight, then I can eat it. Okay. And if I able to eat it, then I will like release it. So this one is called the critical section. So I don't care with the actual function we are executing, but it's okay, we are able to read it. So once we're able to read it, then we need to do the signal. So if I give you the sample, let's say I have a weight function and then signal these two, then how can you do? So I will give you the part of the code like this. Then you need to know how to put it. Okay. It won't really challenging, but you need to refer to it like this. Okay. Think first, maybe like I need to wait. The first one is on my left, and then second I check my right. It's okay. And then I will check, okay, if I'm able to enter the stage, and then I can eat. After you finish compute, then I need to release that, put the false back. Okay, so it works. Also, we have one more. Let's say we have created rooms. So let's say we have a multiple rooms, and we can need to set a room. So in this room, you need to wait. So we will check one more the room, and then do the signal, release it. So you will see the structure for the same method. So it will be like this. And also we have the monitor. Trying to if you remember when we using the monitor, we have the C rate, and then also with the C signal. So also like get the access and waiting for it. For this one, for we try to get the fork, we'll check that if the left will be the PID and the right will be the PID modules by 5. You see doing it because it's a round table. So it's possible that for the array, for the next one is over more than 5, then I will go back to the beginning of the array, start from the index at the beginning. So I will check, okay, my left-hand side, do I have a fork? Okay, no, if we say, okay, therefore, if the left is a fork, then if we will wait for it. Ready. So yes, and then I'll make sure change it to false. So then we will grant it. Okay. Then later we will check the right hand side. How about right hand side? Okay. Then if no, we just the C rate. If we can pass it, then we can change the right to false. Then that means we can use the get the fault from the left hand side, right hand side. The similar idea. And here's like get, then later we need call the one is called the release the fork. So we need also check get the left PID and then the right. So I if you remember no, but this one will be the checking is empty. Then I will check that on the left first. So if no, I will keep checking. If no, I will set the fork to left hand side true. If no, I put send the signal. If a signal the signal is like the +1, like because we get C rate minus n +1, and then we will release the right hand side too. So check it's empty. So if it's empty, then we just fork the y is equals to true. If no, I will do the signal, just like +1 by back. So it's how it works. So so far like for the philosopher, so we have the loop like from the first one to the 5th one. So we will have loop and then think about it. First, we will try to get the fork. Okay, can we get it? If yes, then we will let them do it, like just execute some critical session. So once they complete, just release it. Okay. So you see the main for the user right here, processor always the same. Just like we need to apply which algorithm. Are we using monitor or the segmental? Okay, so which one? Here's you need to memorize the structure. Like if we are using segmental, then what's the code we need to put? Like wait, and then do the signal. Or using monitor, we need to using the C rate. And then because like for C rate, we need to like minus it. Okay. And then after we release, like we need to using a C signal to release it. C rate to get it and C signal to release it. Then about the concurrency mechanism in the modern OS right now. So we need to look at it. So right now we provide different type of mechanism right here, interprocessing, communication or synchronization, we including the pipe, message, share memories, and all the signals. For the pipe, so it's the buffers allow like to process like communicate on the like producer and consumer mode. We have the first in first out queue, so we turn one processor and then we buy another. I think in the previous PowerPoint, we have the one consumer. So if you remember that we have the buffer. So we read one and take one, right? And the message. So message is the a block of byte, like. So this one provide message, send, and then message receive system call. So this one will engage the message passing. So associate which process with the message queue. So it's for the mailbox sample in the previous lecture. And then we have one is called the share memory. So it's the fastest form of like interprocess communication. So we have a common part of virtual memory. So we will share by multiple processes. So all the permission is read only or read write for the process. Okay. Also, here's one example. Like let's say I can only read and somebody can read write, and then we can allow them to change the value but once. So the mutual exclusion and constraint are not like part of the shared memory facilities, but must be provided by the process using the shared memory. This is how it works. And for the same method, right here, the generalization of the same weight and also the same signal. So we just like put in, if we want to get it, we need to like put the same weight first. If we can pass it to the critical section, and after we need to release it with the same signal. Then for the signals, like for the software, so inform the process of the occurrence of a synchronous event. So it's kind of similar. So as an interrupt, but it do not employ the priority. Okay. So this one just like develop update a field of process table. The process which the signal is being sent. So right here we will like respond by signal by, let's say, perform some default action, or signal handle function, or like just ignore the signal. So it's possible. Here's all the signals where we show, like, let's say 0, 1 to 19. So let's say if I send a signal, we have a signal hand up. So right here, or like interrupt and or quit. So all these. You don't have to memorize the signal numbers. Just need to know we have a certain signal to show it. And then what we're going to do is like mainly based on this signal, are we taking some action default, or like when we have this one, then what should we do maybe for certain function to handle it? Or if I have this signal, I can just ignore it. I don't have to take care of it. Okay. Okay. And then for the Linux kernel, so the kernel we know is that like the fundamental layer to handle with the hardware. And then we're including the pi message, share memories, and other signal. There's one more thing we should set up like concurrent mechanism, specific like intended use of is executing in the kernel mode. Okay. Atomic operation. We always say atomic operation is the safe like do as once, like without interruption or without the interference. So the simplest state approach to kernel synchronization. So if the integer operation, the bitmap operation, so all these like will be the atom set. So right here will be like if we say most of the time we apply the atom is like maybe for load or store. These two. You see right here, like when we read the integer, so we will load the value, set the integer, so it will be store stage, add, load, and read and store it. So most of them will be the atomic. So we will not allow interrupt. We'll make sure the data will stay the same. And then we have the spin lock. So it's also the technique to put the critical section in Linux. So how the spin lock is mainly just like only one thread at a time. So any other thread will keep trying like spin until it can occur the lock. So we build on the like integer location in the memory, also check by each thread before it enter the critical section. So we check it. And also we need to make sure like effective situation where the wait time for occurring the lock is expected to be very short. Okay. So what's the disadvantage of this one? The lock thread continues to execute in a busy waiting mode. So we just like keep waiting. And then can I build this one? We call it spinning. So build every time only one thread can able to occur, just like execute one time, get it. That means others like keep checking. So we just kind of like fighting for it and get access. So right here, the example of the spinning lock. So we try to get the lock. So if no, just waiting for it, spin lock, we can call it return, and then just like this one, also disable the interrupt on other like local processor, and then more example. And try to cover. And for the same method, right here we have the user level. So we have provided interface is there in Unix SRv4. So and then internally we implement functions so within the kernel. So it will be more efficient than like we call the user visible method. So it's more like in the kernel level and then have a function. And then we have 3 types of like kernel for the kernel. So binary, context, and read write So here's more details right here. For the transitional, we will try to initialize the dynamic create. So initialize first, and then we have mutual exclusion, and then lock it. So when we try to attempt like giving it, so if make sure we don't have a interrupt. And then once we are able to get it, we will give in the same method right here. So we call the function done. And after we have a done, then we try to have a function called try lock. So we give for this one, we return the non-zero value is available. And then finally we call the function up. You will see all the default function right here. So just need to know. You don't have to memorize all the things. So just need to know what the Linux they can call it, like for handle as a method. For the barriers, so we try to like enforce the order which like the instruction are executed. So let's say we have this like RMB like WMB, so we can like prevent the load from being reorder, access the barrier, like prevent the store between write, or like the 1 MB just for load and store. So we have the SMP. So for this one, so SMP is that we call a symmetric multiprocessors. This one we can handle the RMB for the WMB. So we be store and or the MB load and store. So all this. And the last one, the storage data structure right here. Let's say we have the owner, free lock, writer right here. So right here for Samantha, we always like have a wait and then signal. And also we have read write lock or the conditional variables waiters that too. Mutual exclusion lock. So we apply. So ensure that only one thread at a time can access based on the previous example. And the threads will lock the mutual. So they must at least unlock it. So that's what we need to execute. And the thread will attempt to accrue the mutex lock by execute the mutex that enter. So we have different names, changing the different function, CA, C signal or any. So, but we are all or like Samantha wait and Samantha signal. So all these like just everything, just make sure only one process can access. That's a mutual exclusion. That's what you need to know. And default blocking policy, just using the spin lock. So we select execute one and then let others like keep waiting and check spinning. So an interrupt-based blocking mechanism is up. So we can choose. So maintain lock right here, read and write the locks. So we apply. So allow multi-thread to have a simultaneous read only access to objects protected by the lock. Refer to the code we have for the reader. So for reader, we can read anyone, right? For writer, we need to write and write. So when we write it, we are not allow other readers to read it. So need to wait for it. Once I finish the writing, then we can read it again. So for the single thread to access the object writing at a time, but when executing other reader, that's how it works. So when the lock is occurred for writing text on the status, right, called a write lock. So when it's in writing, then maybe for the reader, we will check, is it in writing? Yes, then I will just waiting. Okay, if no, then I can read it. If one or more reader like occur the lock, it stays, it's a read lock. Okay, so when we are reading, maybe we are not doing the writing. So we are once reach the reading is complete, then I will let the writer to execute the write, the critical section. And you never see the Windows 7. I don't think you know what's Windows 7. So XP, you know what's Windows 7? Okay, so Windows 7 and then Vista, and then we have the Windows 10, 11. So it's a pretty common popular OS. So it will provide the synchronization among the threads that part of object architecture. We have the wait function. We just allow to process on execution, and then we will wait for a single object function. So we request like to handle one synchronized object, and then we return what's a specific object in the signal stage. Also time out interval. So always we have it for the timer. So just like for your information, you need just like for Windows 7, you don't have to memorize what Windows 7 is doing. Just let you know we do have a some synchronization. We have the mutex, we have the segmental, also we have the like multiple timers right here for the process. Okay. And so we have like called a critical section. So critical section similar mechanism of this one. This one will be used only the first for single process. So if we have like multiple processor, the code will be attempt to accurate a spin lock. So when we say this one, every time only one thread will be execute and spin lock will keep checking and go back and check. So last resort, if a spin lock cannot occur, so we have a dispersion object to use to block the thread so that the kernel can disperse another thread or processor. That's how it works. And then we have one is called a slim read write lock. So this one is the window vista, we say. That's how it applied the for this one. So it will enter the kernel to block only after attempt to use the spin lock. So we'll check the spin lock. So if we enter the kernel, so we're just like trying to see. Okay, so that's why it calls slim, because normally only require the allocation to single pointer size piece of memory. So just that way. But you just need to know because OS we change it. And then we have the condition variables. Well, Windows have a conditional, so we see then use either critical section SRW for logs. So we need to accrue the execute log. This we always do. All the structure we always get the log, and the last step we release it. With this one we need to predict. Okay, so is it false? Then we will get like the state condition variables. And if we pass the checking, then we will perform some protect operation. Always you see different like mutual segmental or like read write, producer consumer, like C wait, C signal. We need to know how the monitors, like we actually, but everything the backbone or structure, they always get the log and then check condition. We always just like perform some operation, crucial section, and then release the log. So always remember. But based on different we say mechanism like monitor or segmental, then we will change the structure. Have a different way. That's what we need to remember. So which one, like we need to put the weight, or like what's the name? Same weight or C weight. So you need to know. And then we have called the lock-free synchronization. So we always like rely heavy on the interlock operation of synchronization. So we will operation using hardware facility to guarantee that memory location can be reached, modified, and returned in a single atomic operation. So we will have a hardware, because atomic, that means we mainly focus for the, what you need to know is store and load for this atomic. So we cannot interrupt. So many things. So mainly actually I go through everything about the deadlock. So deadlock is like we will block a set of process. So what you need to know is like why we will enter a deadlock. So we are waiting for other resources, right? Okay, then if we have the deadlock, then we need to know what are the possible ways to avoid. No, we have the prevention, we have avoidance, right? And then also, if really enter the deadlock, how can we do the recover? Okay, so how can we predict? So during it, and then just need to know if we need to do the prevention, how should I slightly you need to remember the definitions like, okay, so for deadlock, what's the prevention? Just make sure it's not occur. But for detection, is the checking. Okay, and we need to know but they always have a disadvantage, right? So we need to detect it. Let's say I need to know the early stage. I need to know this process, how many total resources need to get it. But it's maybe this in the beginning, but I cannot increase it later. Also like avoid it. So we need to, okay, let's say I have a new resources or I already execute a process. We are not allowed them. Let's say they need to request a new resources. Maybe we are not allowed them to do that. So you need to do it in the beginning when we initialize it. So then we can avoid that deadlock. So what do you need to know is like mainly look at this summary part is like think about, okay, possible way to create deadlock and then how can we prevent it is the strategy. Some definition, yeah, just like remember some definition from the PowerPoint. And later I will try to maybe cover in the lab time is like showing some example and then the code, how to execute and then prevent. More like this idea. So CWH, or let's say we will discuss like next time about the table one table. So if the left hand side, because I think I just like quickly go through it and then show you the source code, but I don't think you'll really catch it, like what's this doing. So you can think about this one and then we can come back for the lab and then we can discuss it. So what's this doing? Just think about you need to use that form, but you cannot use it. And then you can use like actually this condition is that you can either use the for on your left hand side or right hand side, right? Okay. So this one is much more like the circular cube or like circular array. Not really cube, but it's an array. Okay. So we need to check, okay, can I use the for on my left hand side? Can I use the for on my right hand side? Yes, I can use either one to it. Then I can use it. And then I need to make sure I like know of them using it in the same time. Then how can we check it? So because all this like the OS, like all this like algorithm, actually all this already implement, they already able like kind of like to fix the issue. So that's why we just need to remember it and then to understood what is working. Yeah, because you are not really to create something new. But if something for discuss new topic like in the lab, like previous, I forgot that one, share resources, then just I need to ask you to write the pseudo code. You don't have to really implement. Even sometimes if I need to ask the question is that, okay, let's say you need to check. So which one you need to wait? So this one I will check the one, maybe let's say assume one, I start with the left first. Some method maybe like check it, do the wait, check the left, and then check the right. Then you can do the critical like this. Okay. We'll try to cover the details, more details in this one. And let me show you one thing. Because last time we talked about addressing, right? So addressing, I tried to create a source code. In the previous lab, so I just take the last time, you can look at it. I will upload this part. So actually pretty simple about addressing. So in the memory, so if we have a called direct address, so I just like pointing to that one item. So you see, like if I have a direct address, so passing this one, so I just memory location 3. So it's pretty straightforward. But if we have called the indirect, that means I have a pointer. So I need to get a pointer, and then pointer to the array for that position. This one is the simulation to working in it. If you working on the C purpose, you will look like maybe other language. If you say array and then with the index, so that one we directly access it. But if we are using a pointer, then we will like first. I'm not so sure if you know something like this. If I have an array, sometimes I'm pointing this. Have you ever seen something like this? Okay, yes, like this, yeah. So you are always saving the address, like the value right here. Actually, is the address of the memory. So that's what we call indirect. And direct is just access the index. Yeah, so actually, programming actually is not complicated, but in the lecture, you see lots of definition and go through the slides. So once you know this one, you're good. Okay. And we have different mode of it. I will upload the code for you to look at it. And for the direct indirect, sometimes we were doing like double indirect addressing. So like I use the one pointer and I put to another pointer and another pointer to execute. So but this one is like simulation, so it's pretty straightforward, but I will execute and then you can look at it. And I will execute the addressing mode, this one directly. Actually, in my source code, I will just like create a site value timestamp. So if I directly access it, so will be the value, and if maybe too small. So for the indirect access, so I will create a pointer, then I will point to the memory location. Maybe it's pretty small to you, but I will upload this source code so you can look at it. So if you have an idea, knowing what's the link is, then you're okay. And then I just like create one more called a double. So the double link is like I use the first pointer, and then pointing to one more. So it's apply the same theory, but I just like using one more pointer to pointing to my target. And it will be that's it for the called a double pointer, one more. But if we are pointing to something in weighted range, it's error. We are not allowed to set it, because this one is for the memory size, we just set to 20. So let's say I want to access to 25, it fails. Okay. So here is just an example showing how was the addressing in our previous lecture, like talking about addressing. And that's it for today's class. Thank you. I know it's something boring, but I try to give you some example you can execute.